Now, since you all have an idea of the model itself, how do I go about optimizing the system? What is the big overall view? Well, you can think about this chart as, well, I need an input, I need a model, and I need an output. Inputs here are the ridership demand, and all these six inputs, system physical profile until the queue length. The model, the one that you saw, is the box here, the model and simulation. And I need variables or performance metrics to characterize the system. And that is through the figures of merit. In order for me to compare which one is the best. And finally, I can do, if I have this, I can now analyze and I can get the optimal solution. First, I have to be concerned about how fast can a sled go? What is the fastest speed? Well, there are top speeds, but for me to use, I need to use kinematic equations. I need to come up with the jerk, acceleration, and velocity values. So I use MATLAB, and as you can see, the sled trajectories were obtained using this software, MATLAB. What is important is the transit times. You can see in this chart, on this left side, you have maximum, nominal, minimum. You have TED to web station. You have web to power time and TED to power time station. You have speed and transit times. Now, I'd like you to focus your attention on this yellow column, nominal. This is my objective. I have to come up with the transit times for my model. So I obtained TED to web as 35, web to power time as 41 seconds of travel time, and for TED to power time I need that travel time of 57 seconds. What is important to note here is using the kinematic equations I used earlier, I was able to get the maximum value or the maximum speed possible, which is 24 meters per second. But you don't have to go all the way up 24 meters per second, because it's like speeding and then suddenly you brake. So you need some cruising. You need to cruise. So the nominal speed that I chose is allows some cruise speed, but doesn't sacrifice the transit time. Notice the difference between when you travel for 24 meters per second with the 20 meters per second, you only have 1 second difference. So that is basically the method I use to obtain these nominal values. Now that I know how fast my sled should go, I need to know the input of passengers to the system that you just saw earlier, the model. So this is a condensed form of all what I shall term as ridership demand. The ridership demand is nothing but the input of passengers per unit of time, and it can be generally classified into two. You have functions of time and a function of a type of passenger. If it is demand as a function of time, imagine a whole semester. In my study, I generalized 4 categories of movement of passengers in ODU. You can have class peak, which is the main motivation for using the MATLAB. Off-peak, special events, and mealtime. For class peak, I want to acknowledge the business group. They're still not here, but they were able to provide this for my study. And this other return between classes, all the events that you can think of that will motivate a passenger to use the MATLAB is in here. So that's for class peak. For off-peak, those movement of passengers which is not under class peak or special event mealtime. Special events, as was discussed earlier, about events in TED Constant Center, primarily about basketball events. Mealtime, well, during breakfast, lunch, and dinner. Another category for ridership demand is type of passenger. You can categorize students as commuters, residents, and faculty and staff. Now there is a black and red portion here. The black ones I just like to acknowledge that those are came from the ridership study provided by the business group. The other ridership demands, I had to consult subject matter experts and do more research in or literature review to be able to obtain the other ridership demands I need to model the system. So I keep talking about ridership demand. What is that? So it is the inter-arrival passengers. But for me to use it in the model that I showed you earlier, it needs to be in a form that can be directly used into the model. And it should be in an input inter-arrival distribution form. Or from here onwards, I'll call it lambda. So lambda is nothing but expression of seconds in between arrival per passenger. So you can see in this x-axis, say for example, a lot of passengers arrive 5 seconds in between each other. So that describes the probability that more of them actually arrive 5 seconds per passenger. So this is sort of like provides you the average inter-arrival rate, except that it is modeled using exponential. Now there are different types of input distributions. You have Y-vo, gamma distributions, but since we don't have real-world data, I used loss or simulation modeling analysis book and he stated that exponential is the best inter-arrival distribution you can use for this kind of study. Now, the ridership demand, where does it come from? So the next few charts just show you that I considered all the population. So this is ODU. I have numbered the residents. You can see the total. This is the track. This is the Palatine end. This is Web Center. This is exactly where we are. And that shows you just the student resident population. So I totaled all the population, because that is my source of ridership demand. And this chart shows you that there are approximately 23,000 personnel in ODU composed of the different students, faculty, and staff. Now this value changes. So those values are approximations. And another important concept that was obtained from the ridership study is the intention level. The total student population, when the ridership study was made, it was found that, you want to learn who wants to use the maglev. That's this chart is showing. 7 being the highest. I will definitely use the maglev. So that is in reference to the ridership study conducted. Finally, for one more thing about ridership demand, for off-peak, I discussed already the class, the special events, and meal times. But for off-peak, this is movement, which is separate from the first 3 events that I mentioned. There are 2 categories, as I said: student residents and student commuters. Residents will move once every 7 days. Well, this is just an arbitrary assumption. It can go lower, it can go higher. And for the movement for student commuters, there are 17,000 student commuters. And I assume, since they are outside the campus, they will use the maglev for whatever purpose, at least once a semester. So I know now that how fast my sled goes. I know my ridership demand. I built my models, the one that you have seen earlier. I have done 11 modes, and the most important of which are